Blasting off to a career. Today, NASA tried to recruit the next generation of STEM students.
When students think of space, they think engineering, aerospace, physics, but today NASA is showing those same students that they don't need a
The announcement came from NASA's Propulsion Research Division with an uncharacteristic air of finality. After decades of speculation, failed prototypes, and concepts dismissed as purely theoretical, they confirmed the development of a propulsion system so advanced that it could, at least in theory and now in their testing, reach the speed of light. The statement sent shockwaves through the scientific community, not because the idea of lightspeed travel was new, but because the sheer barrier-breaking nature of it was something many thought humanity would not overcome for centuries. NASA's reveal did not come wrapped in cautious words or hedged in complex disclaimers. It was a clear acknowledgement that what once belonged to science fiction had been pulled into the laboratory and tested under the relentless scrutiny of experimental physics. Before we start, smash the like and subscribe buttons for more updates. The core of this breakthrough rests on a propulsion concept unlike any that had been attempted at this scale before. Rather than relying on chemical propellants, nuclear energy, or even advanced ion thrusters, the system manipulates spacetime itself. At the heart of this design lies a technology that bends the very geometry of the universe, contracting space ahead of the craft and expanding it behind. This principle, once limited to mathematical speculation, has been refined into a working engine through a combination of ultra-precise energy control, quantum field manipulation, and materials science that operates on scales previously deemed impossible. The result is not acceleration in the traditional sense, but rather a controlled movement of spacetime, allowing the vessel to remain in its own frame of reference while the universe shifts around it. The implications for such a capability are staggering. Reaching light speed with this method means sidestepping the insurmountable mass energy requirements that would plague any craft trying to accelerate in the conventional way. No colossal fuel tanks stretching for kilometers, no fusion reactors tearing themselves apart under strain, just a self-contained power system that uses principles embedded in the fundamental structure of reality. This approach turns interstellar distances from daunting multi-generational journeys into trips that could be completed within a single human lifetime. The leap from exploring planets in our solar system to stepping onto the shores of worlds orbiting distant stars becomes not a dream but a logistical question of where to go first. What makes this announcement even more extraordinary is the fact that NASA's researchers were not chasing light speed directly when they stumbled upon the key mechanism. The original experiments involved manipulating quantum vacuum fluctuations to reduce resistance in microscale spacecraft models. These tests revealed subtle distortions in space-time geometry around the apparatus, deviations that couldn't be explained by known physics. The team refined their models, built more precise instruments, and soon realized they were detecting the earliest signs of what would later become the propulsion effect. Months turned into years of refinement, the engineering challenges stacking higher with each success, until the system was large and stable enough to move a manned-scale craft in controlled trials. Those trials have been conducted in a strictly monitored environment, a vacuum chamber nearly a kilometer in diameter, shielded from every conceivable source of interference. Within this chamber, the experimental craft was suspended in magnetic fields to eliminate contact friction, its systems running autonomously, while sensors tracked every photon, particle, and gravitational ripple. Observers watched as the craft did something no human machine had done before. It shifted its position in measurable increments without any visible thrust, exhaust, or mechanical motion. The data revealed that within a fraction of a second, the craft had displaced itself in a way consistent with manipulating the underlying structure of spacetime itself. Once scaled up, this effect would allow for a steady, controllable movement at velocities that, to an outside observer, could approach the speed of light without breaking the laws of relativity. What this represents is more than a new way to move. It is a new relationship with the universe. Lightspeed travel has always been the cruel boundary line for technological ambition, a wall built by the equations of Einstein and reinforced by every practical engineering limitation humanity has encountered. To brush against it now is to rewrite not only our capabilities but our sense of place in the cosmos. The stars are no longer distant points of light in the night sky. They are potential destinations. The immense gulfs between systems shrink in conceptual scale, making our galaxy feel less like an unreachable tapestry and more like a map to be navigated. The reaction among physicists has been a mixture of awe and stunned recalibration. Many who had spent their careers arguing that light speed was an unassailable barrier are now revisiting their assumptions. Others who quietly nurtured the hope that exotic propulsion might one day be possible find themselves vindicated in ways they never dared to expect. This shift is not only technological, it is philosophical. If space can be traversed at these speeds, the human species is no longer bound to the evolutionary island of Earth. Civilizations could spread to the stars, not in theoretical speculation, but in a foreseeable future. Even within NASA, the realization has cascaded across departments. Astrobiologists are already drafting mission profiles to nearby exoplanets, considering what instruments and habitats would be needed to study alien biospheres firsthand. Planetary scientists are rethinking the timeframes for studying the icy moons of gas giants, knowing they could now be reached and returned from with unprecedented speed. Engineers are redesigning habitats and spacecraft modules to match the requirements of this new mode of travel, structures that can withstand the unique stresses of moving through spacetime warps while keeping human crews safe and comfortable. The technological foundation of the Lightspeed-capable craft relies on materials that barely existed a decade ago. Engine components are built from meta-alloys with precisely tuned quantum lattice structures, enabling them to channel enormous energy densities without degrading. Energy storage itself is achieved through a hybrid system of high-capacity superconductors and vacuum energy reservoirs, systems that operate near absolute zero to minimize entropy. Guidance and control require processing speeds that surpass anything in current commercial computing, with quantum processors orchestrating the delicate balance between spatial contraction and expansion in real time. Every subsystem operates at the bleeding edge of what is currently possible, and in several cases, beyond what was thought achievable at all. While the propulsion method does not technically violate relativity, its operation plays in the margins of physical law where even small errors could cause catastrophic instability. The engineering safeguards are as monumental as the propulsion itself. Fail-safes that can instantly collapse the warp field, redundant containment systems to prevent quantum vacuum collapse, and continuous environmental monitoring to ensure the craft does not inadvertently distort surrounding matter. NASA's testing protocols have been exhaustive, with hundreds of simulations run before each experimental activation, ensuring every parameter remains within tolerances. The knowledge that a craft can reach light speed has transformed the idea of space exploration into something more akin to navigation across oceans. Distances that once required decades of travel, like the 4 light-years to Proxima Centauri, now fall within a range that could be covered in a practical mission timeline. This changes how humanity might approach the search for life, the mapping of stellar systems, and even the colonization of other worlds. Entire mission architectures, from crude research vessels to automated cargo ships, can now be imagined without the crushing burden of multi-decade isolation. From a geopolitical perspective, the possession of such a technology redefines the very meaning of strategic advantage. The ability to traverse interstellar space at light speed is not just a scientific triumph, it is the ultimate extension of mobility, exploration, and reach. Although NASA's announcement framed this as a scientific breakthrough for humanity as a whole, the underlying reality is that any entity controlling such a capability holds a position of influence unmatched in history. In the context of exploration, it means the first to deploy such craft can lay claim to discoveries, resources, and knowledge on a scale impossible to measure. Culturally, the knowledge of light-speed travel challenges deeply rooted narratives about human limitation. For centuries, the stars were symbols of unreachable wonder, a backdrop to human existence rather than a stage upon which it could unfold. With this development, they become places, not just poetic metaphors, but physical destinations with terrain, weather, and horizons of their own. The psychological impact of knowing that entire solar systems can be reached within a single human lifespan is immense. Generations that grew up watching depictions of starships in fiction will see them take shape in hangars and laboratories, no longer as dreams but as projects with launch schedules and crew rosters. The science behind the propulsion is not only a tool for travel, it also opens pathways to new physics. The manipulation of spacetime in a controlled environment creates opportunities for experiments that could probe the nature of gravity, dark energy, and quantum fields in unprecedented ways. Each test flight is not just a journey but a scientific instrument in its own right, gathering data from regions of spacetime altered in ways never before possible. This feedback loop of exploration and discovery has the potential to accelerate not just space travel, but the very pace at which humanity understands the universe. The sheer audacity of what NASA has revealed cannot be overstated. The technical hurdles they have overcome, stability in the warp field, energy generation and containment, the precise modulation of space-time curvature, represent a summit of engineering that stands alongside the invention of the rocket or the microprocessor. What makes this achievement singular, however, is that it directly confronts one of the most fundamental constraints in nature. To reach light speed is to match the universe at its own ultimate pace, to move at the threshold where time itself stretches and bends. In the days since the announcement, laboratories and observatories around the world have been recalibrating their priorities. Universities are revising course structures to train the next generation of physicists and engineers who will work on refining and expanding the technology. Private aerospace companies are making overtures for collaboration, seeing in this breakthrough the seed of a new era in commerce, transport, and even industry beyond Earth. While the propulsion system is complex and requires exotic materials not yet produced at industrial scale, the process of scaling up is already being discussed with an urgency rarely seen in peacetime research. The symbolism of Lightspeed capability extends beyond its technical merits. It represents a point in human history where our species takes a definitive step from being confined to a single star system to becoming a galactic traveler. It is a moment that could be remembered as the true dawn of interstellar civilization. The craft now sitting in NASA's test facilities is more than a machine. It is a key to a new era, a tool that collapses the immense silence between the stars into a corridor we can traverse. NASA's scientists have long said that the greatest barrier to exploring the cosmos was not distance itself, but the limitations of our own methods. With the creation of a Lightspeed-capable engine, that barrier has been breached. The gulf between dream and reality, between stargazing and star voyaging, has narrowed to the point where the two are becoming indistinguishable. And in that narrowing lies the greatest transformation of all. The shift from wondering what lies beyond our small corner of the galaxy to preparing to go and see it for ourselves. The internal documentation surrounding the Lightspeed project reveals a progression of engineering milestones that, while astonishing in their own right, are overshadowed by the sheer scope of what they collectively accomplish. One of the earliest stages involved the stabilization of micro-warp fields. These were fragile constructs prone to collapsing into nothingness or worse, spiraling into chaotic distortions that threatened to destabilize the testing chamber. The key breakthrough came with the development of a dynamic field harmonizer, a device capable of adjusting curvature in real time based on quantum-level fluctuations. This harmonizer acts much like a conductor leading an orchestra, ensuring that every oscillation in spacetime remains in perfect synchrony with the rest of the system. Without it, sustained lightspeed travel would be impossible. With it, the pathway to extended journeys opened in an instant. This harmonization process is more than a matter of precision. It is an exercise in balancing immense energies at the threshold of natural law. The warp field requires a controlled asymmetry, with spacetime contracting ahead of the craft and expanding behind it. This asymmetry is delicate. Too much contraction, and the stresses on the craft become intolerable. Too much expansion, and the field destabilizes. The harmonizer not only maintains this balance but adapts it based on the surrounding environment. In interstellar space, where gravitational gradients are minimal, the field can remain relatively stable with low energy consumption. Near planetary systems, where masses distort spacetime naturally, the harmonizer shifts into a more active mode, recalibrating the field in fractions of a nanosecond to maintain safe passage. NASA's engineers quickly realized that this adaptability would make the technology not just a vehicle for deep space travel, but a versatile transportation system capable of navigating diverse gravitational environments. A Lightspeed-capable craft could, in theory, traverse vast stellar gulfs and then enter orbit around a planet with smooth, calculated precision, emerging from its warp envelope directly into a stable trajectory without the need for large orbital correction burns. This efficiency redefines mission planning. Journeys once dominated by complex delta-v calculations and lengthy braking maneuvers are replaced with direct calculated insertions into the desired location. Beyond navigation, the very structure of these spacecraft has undergone a radical reimagining. The hulls are no longer merely protective shells, but integral components of the warp system itself. Every panel, frame, and joint is constructed from layered metamaterials embedded with microscopic field modulators. These modulators interact directly with the warp envelope, fine-tuning its boundaries and ensuring that the craft remains perfectly encapsulated in a bubble of normal spacetime. This not only protects the vessel from external distortions, but also shields it from the lethal radiation and high-energy particles that would otherwise be encountered at such speeds. In effect, the warp envelope serves as both propulsion and protection, a combined function that reduces mass and complexity compared to traditional spacecraft designs. The crew environment inside such a vessel represents another leap forward. Since the ship moves within its own bubble of spacetime, the crew does not experience the crushing accelerations that would accompany conventional near-light-speed travel. Instead, the sensation is one of smooth, continuous movement, with no more strain on the body than riding in a modern passenger jet. This makes extended voyages both physically and psychologically feasible. NASA's habitability teams have already begun designing living spaces that blend the functionality of research stations with the comfort of long-duration habitats, knowing that crews will be spending months or years away from Earth, not because of distance, but because of the scientific depth of their missions. The propulsion breakthrough also forces a reconsideration of our approach to time. In relativity, approaching light speed causes time dilation, a phenomenon where time passes more slowly for the traveler than for those left behind. The warp approach, however, manipulates the geometry of space rather than accelerating the ship through it, meaning that the traveler's time passes much more in line with that of observers elsewhere. This eliminates the time gap problem of relativistic travel, ensuring that crews returning from distant systems will not find decades have passed at home. The implications of this are profound. It maintains continuity between interstellar crews and their home societies, enabling missions to be part of an ongoing, evolving exploration effort rather than isolated events. The moment this capability was demonstrated, it became clear that our perception of the galaxy itself would need to evolve. Astronomical catalogs, once abstract repositories of star positions and spectral classifications, now resemble navigational charts. Each nearby system is not just a point of light to be observed from afar, but a potential destination to be visited, surveyed, and studied. The universe has always been vast beyond comprehension, but now its scale has shifted in human imagination, from infinite remoteness to an archipelago of reachable worlds. The maps we once used to gaze upward will become operational tools for charting voyages, recording landing sites, and marking regions of scientific interest. The scientific potential is staggering. With light-speed travel, missions to distant exoplanets move beyond passive observation. We will no longer rely solely on analyzing faint spectrographic lines for signs of life. We will be able to send instruments directly into alien atmospheres, scoop samples from extraterrestrial oceans, and examine geology firsthand. Planetary systems with unusual orbital dynamics or exotic chemistry will be open for direct exploration, giving us insights into the diversity of planetary formation and evolution that our solar system alone could never provide. Even worlds without life hold value, serving as natural laboratories for testing theories of physics, chemistry, and planetary science under conditions impossible to replicate on Earth. The same technology also offers new methods for studying cosmic phenomena that were once purely theoretical playgrounds. Imagine positioning a craft just outside the event horizon of a black hole, stabilized within a warp envelope, to study relativistic jets in exquisite detail, or placing observatories in the deep interstellar void between spiral arms, far from the interference of galactic dust, to peer into the cosmic microwave background with unprecedented clarity. Lightspeed travel changes the nature of astronomy itself, from a discipline conducted almost entirely from a distance to one that can position its instruments wherever the phenomena are occurring. The energy source that drives this propulsion is itself a marvel. While the specifics remain tightly guarded, what has been shared suggests that the system draws upon controlled extraction of vacuum energy, a form of energy that permeates space-time itself. This is not an infinite power supply, but its density and stability are such that it can sustain the warp field for durations measured in years. The engineering required to tap into this resource involves creating a stable energy aperture that channels vacuum fluctuations into usable electrical and magnetic power without causing runaway reactions. The containment fields for this process are a technological achievement rivaling the warp system itself. There are already discussions within the engineering teams about scaling the system up for massive vessels. While the current prototypes are designed for crews of perhaps a dozen scientists and pilots, there is no theoretical barrier to constructing ships capable of carrying hundreds, complete with laboratories, manufacturing facilities, and agricultural modules. Such vessels could serve as mobile research stations, diplomatic envoys, or even the first steps toward permanent off-world settlements. The mobility provided by Lightspeed capability ensures that such stations would never be isolated. They could return to Earth for resupply or reposition themselves to study new targets as needed. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on NASA creating technology capable of reaching light speed? We want to hear from you. Thank you for watching, and see you next time.